Hi, my name is André Zenner and I'm a postdoctoral researcher at Saarland University and the German Research Center for Artificial Intelligence in Saarbrücken, Germany. In the following, I'm happy to present our paper, Induce a Blink of the Eye, evaluating techniques for triggering eye blinks in virtual reality. This paper has been joint work together with my co-authors. Virtual reality is a technique that simulates a virtual environment to us by stimulating our various biological sensors in ways that make us experience a sense of presence. As such, virtual reality is tuned to trick our perception. Yet sometimes also our perception can trick us. Consider, for example, the virtual environment depicted here. Now look at the environment closely again. Did you notice something? In fact, several changes just happened inside the environment, but chances are that you have missed some of the manipulations. Such changes, while easy to spot when we see the modified and unmodified scene in quick succession, are likely to go unnoticed by us due to a perceptual phenomenon known as change blindness. Change blindness is a great opportunity for virtual reality to introduce unnoticeable scene manipulations and occurs, for example, when our view of a scene is briefly occluded, such as during eye blinks, which blind us for around 150 milliseconds. As such, change blindness has seen numerous applications in the past, such as for redirecting the user's walking path and reaching motions. Thus, blinks are a valuable tool for illusion techniques in VR, as they provide opportunities for change blindness on a regular basis, on average every 3 to 6 seconds, which is great if enough time to wait for the next blink is available. But what if blinks are required within short time windows? For example, when blinks are used for redirected reaching, where interactions only take up to 2 seconds. To grant the VR system control over the user's blinking behavior, we propose and investigate different methods to trigger blinks on demand, which are specifically tailored to virtual reality. Inspired by the use case of blink-suppressed hand redirection, we formulate 4 central requirements for successful blink triggers, namely effectiveness, efficiency, reliability, and unobtrusiveness. Looking at the related literature, triggering blinking is not an entirely new topic. 2 previous works have studied software and hardware-based techniques to trigger blinks in desktop and wearable setups, but no work has yet considered the use case of virtual reality. Previous systems were designed to combat the computer vision syndrome and thus focused on increasing the user's average blink frequency over time with relaxed time constraints. To investigate on-demand blink triggering in virtual reality, in this paper, we build upon the findings of previous research and transferred established triggering techniques to the domain of virtual reality while also proposing a novel trigger method. Specifically, we started out with 6 different triggers derived from a set of well-known blink reflexes. Following extensive pre-testing and parameter tuning, we filtered for the most promising approaches to compare them in a user study. During this pre-testing phase, we decided to dismiss 2 initial trigger concepts and arrived at 4 final blink trigger methods demonstrated in the following video clips. Firstly, we investigated a software-based flash trigger that targets the dazzle reflex. This reflex makes us blink when a bright light shines into our eyes. To take advantage of the dazzle reflex, the flash method renders a white frame inside the HMD when the trigger is activated to maximize retinal illumination for a short time, simulating a bright light. Secondly, we explored a software-based blur trigger that gradually blurs the user's virtual vision. By this, we simulate dry eyes and evoke the need to blink in order to regain clear vision. Thirdly, we proposed a novel software-based trigger method called the approaching object trigger, which is unique to virtual reality. This method targets the menace reflex and renders a small black sphere that rapidly approaches the user's face in order to trigger a protective closing of the eyelids. And finally, we also considered a hardware-based air puff trigger that makes use of the corneal reflex. This trigger stimulates the cornea with a gentle puff of air blown next to the user's left eye to trigger a blink reaction in both eyes. To implement the air puff, we integrated a microblower into the HMD. We conducted a user study with 18 participants to compare our 4 trigger methods. In order to prevent bias, we only revealed that the experiment was studying blink triggers after the study. The task in our experiment required participants to play a simple color remembering game, during which they had to reach forward with their hand for 140 times. Each trigger was randomly activated in 12 trials, and in the remaining 92 trials, no stimulus was presented, which served as the baseline. After each trial, participants were asked the yes-no question, "Did you notice any visual or physical stimulus?" and rated on a 5-point scale how much they felt distracted by a stimulus. Looking at the results of our study, we found the blink response time to differ significantly among the methods and conclude that the approaching object, air puff, and flash triggers are generally effective in triggering blinks on demand. The blur trigger, in contrast, did not yield quicker blink responses than our baseline condition, in which no trigger was activated. Overall, the approaching object trigger, which is unique to virtual reality, showed the shortest response times and only small variation across participants, rendering the menace reflex effective and efficient and hence highly interesting for virtual reality. Considering the reliability of the triggers, only some of them were found to be reliable for hand redirection. We found that only the approaching object and air puff triggers can be recommended when blinks need to be triggered within time windows of only 1 second. Since our initial goal was to develop unnoticeable triggers, we also looked at the results on noticeability. Here, however, we conclude that when configured to be effective, all our triggers were easily noticeable. As a consequence, it seems important to consider as how obtrusive triggers are perceived. We found the triggers to differ in distraction, with the most effective approaching object trigger being perceived also as most distracting, and all other triggers to be perceived as significantly less distracting. The participants' performance in the game task was not found to be impacted by any trigger. We summarize our findings in a decision tree designed to help researchers and practitioners in finding the most suitable triggers for their VR use cases. Overall, we found the air puff trigger to constitute the best compromise between performance and comfort, with the downside of requiring additional hardware and a per-user calibration. We recommend the air puff trigger when fast blink responses and low distraction is required. To improve its usability, future research should consider using eye tracking to automatically calibrate the air nozzle. As a software-based alternative, we identified the flash trigger, which was similar in performance and distraction to the air puff trigger, but not always quick enough to trigger blinks while reaching. To improve this trigger, different flash patterns and brighter displays should be tested. In use cases where fast responses are required, but distraction is not a primary concern, our findings show that the approaching object trigger is most suitable. While distracting, it performed best in terms of reliability and triggering performance. Future work should investigate if distraction can be reduced, for example, by tailoring the stimulus to the logic and aesthetics of the virtual environment. And lastly, we found the blur trigger to be suitable only in cases where neither response time nor distraction is of concern. Yet the blur trigger seems worthy of further investigation, as it showed the potential to go unnoticed, with one participant having not noticed the trigger at all in our study. In conclusion, we found that effectively and efficiently triggering blinks in VR is possible, even on demand and reliably during time-critical interactions like reaching. Yet we also conclude that presented triggers will almost certainly be noticed by users and are generally perceived as distracting, with different trigger methods leading to different levels of distraction. Given these findings, in future work it is important to study how triggers can be made more comfortable while maintaining triggering performance. For this, it seems worthwhile to combine different triggers, potentially each with reduced intensity, to study habituation effects and ultimately to investigate how redirection techniques and blink triggers integrate in practice. For more details, please refer to our paper. Thank you.